one of the organizers.
I see. I see. I see. So let's start. I think we are on time. So, okay, so very warm welcome to all of you. So today we have Siddharth Barman from Indian Institute of Science. Siddharth is in the Computer Science and Automation Department at ISC, and he will talk about algorithms for fair cake division. Siddharth, you will have 75 minutes, and you may take questions as you go along.
Yeah, please. It'll be easier for me if you can just unmute yourself and ask questions. This way, you don't have to keep monitoring the chat window. So let me start by thanking the organizers for this invitation. I'm very happy to be virtually at ISI Delhi. Um, I will talk about a recent joint work with Nidhi Rathi, and the work stands at the interface of theoretical computer science and game theory. And so this is sort of a somewhat of a again area that's in its teenage years. This area of algorithmic game theory, and the story of this field has been a story of impressive bad news. Many of the central solution concepts in game theory that are supported by universal existential results turn out to not have like computational turn out to not enjoy computational tractability, and this story arc sort of repeats itself in the fair division literature. So in particular, where we have many classic results that sort of guarantee meaningful existence of fair divisions, meaningfully fair divisions of resources in many settings. At the same time, these existential results do not have algorithmic counterparts. So in summary, the story so far has been like, okay, while we do know that fair divisions exist, I'll define formally what all these means. While they exist, finding them is a challenging task, and in some cases, and as I'll point out, in fact, there are very strong negative results of the form that there could be no finite time algorithm, or there are other hardness results that sort of imply that it's quite unlikely that there will be efficient algorithms for finding sort of fair solutions that are guaranteed to exist. So what I'll do today is present a result that circumvents these hardness results, circumvents these barriers by looking at interesting subclasses. So we'll identify a relevant subclass of instances and show that for this interesting subclass under this sort of focused attention, we can design efficient algorithms, we can sort of bypass these computational hardness results. Okay, so the takeaway, as I said, is that we will develop algorithms that complement existential results that are innately non-constructive. And while the talk will be bit on the algorithmic side, I do want to emphasize, and this is probably a good meta takeaway, is that interesting algorithms and new algorithms actually stand on the shoulders of new existential results. I will come back to this point and sort of substantiate it in the in our result. But this is a recurring theme that it's been observed. Like if you want to design new algorithms, or in fact, if you want to design algorithms, many times you have to revisit the existential result itself, and then like either come up with a new one or try to understand like how to constructivize it. And a lot of results in game theory are like by nature non-constructive, things that follow from say fixed point theorems and such. They're not in and of itself, they're not amenable to like algorithmic results. So this is this sort of harmony between existential results and algorithmic results is like at a high level is what I want to emphasize or focus on. Okay, with that in mind, let me just also mention that while the talk is going to be technical and focus on it's going to be a theory heavy talk. there are like good reasons for studying algorithms for fair divisions, algorithm for the kind of problems that I'm going to talk about. And the motivation comes from these online platforms such as splitit.org that sort of provide solutions or scalable methods, and they're widely used. So this sort of applicability of fair division methods is in part sort of motivation for developing algorithms, and not just saying that okay, good, there are fair solutions, good. What these platforms require is actually to find them, and hence we have to look at algorithmic solutions. So I'll pretty much not talk about these applications in the talk. I'd be happy to talk about them offline and like other sort of more broader objectives in this sort of arena. Okay, so the focus of our talk is going to be on the division of, or on the partitioning of resources that are divisible and heterogeneous. So that's they're typically referred to as a cake. The resource is going to be divisible in the sense that it will make sense to say that 1/3 of the resource is assigned to some person and 2/3 of it is assigned to some other person. So I'm going to deal with resources such as land, water, transmission spectrum, or processing time on a machine, which can be fractionally assigned, and hence the word divisible. Plus, we'll look at we are going to assume that the resource at hand, the resource that has to be fairly divided, is heterogeneous. Heterogeneous in the sense that different parts of the resource are valued differently by the participating agents. So this is referred to as a cake. So the cake is divisible. I can cut it into pieces, and it's heterogeneous in the sense that like part of the cake might have chocolate, which would be preferred by some people. Other parts might have vanilla, which would be preferred by others. So this is the cake is the usual reference to a divisible heterogeneous resource. But more generally, you can think of settings like division of land, say transmission spectrum, and so on. So,
Siddharth, I just had a clarification. So
yes.
is it here that, is it the fact that, let's say the cake was basically homogeneous in the sense that it was just a cake? Is it that different agents have different kind of likings for the cake, or does it have to be like the cake is itself very disparate, or is it equivalent?
I believe it's equivalent. Like, let me just give me 1 minute, and I'll tell you the sort of the cardinal preferences, and if
That's
that
fine.
doesn't
I'll
answer
wait.
the question, we can circle back to it. Yeah. So I'm not going to deal with the most general form, like you can look at like ordinal preferences and so on. I'm going to pick a standard but cardinal preference model, and just going to work with that. It's just for algorithmic purposes that kind of you do need to have such an anchor. So this is a extremely well studied uh, problem. This cake cutting literature has been there for now decades. In fact, one of the classical results by Steinhaus that laid the mathematical foundations of fair division stems from looking at this cake cutting problem. There are multiple textbooks like devoted to division of cake cutting and like cake division. It's an important topic more broadly in the fair division and collective welfare literature. Many of the classical notions of fairness are developed in this context of cake cutting, and it also plays a important role in the sort of more recent line of work on computational social choice, where that deals more with computational side of things, that deals more with algorithmic sides of things. So like the result I'll present today will be of the latter flavor. It will look at algorithms for dividing or partitioning this cake, this divisible heterogeneous resource, in a fair manner. These are just a very selective list of references. A lot of work has been done on cake cutting literature, like from like pure theoretical side to like its application in dispute resolution, border border disputes and so on. I mean, the classical result, like these protocols of cut and choose, actually have even biblical references. So it's a well studied topic by sort of yeah, with a lot of prior work on it. Okay, so let's be a bit more formal about the model, and this will probably answer the question that was raised about whether the cake is homogeneous or it's just the preferences. So formally, the cake is modeled as the unit interval 0, 1. So the divisibility here is captured by the fact that I can assign sub-intervals of 0, 1 to different agents. So whenever I say agents, I mean people participating in the fair division exercise. So the divisibility here is captured by the fact that different subintervals, different pieces of the cake can be assigned to different agents. And the heterogeneity of the resource is captured by the fact that different agents have different valuation functions. So in particular, I'm going to assume the following cardinal, I'm going to work with this cardinal preference model, and this is again standard in this literature. So what this says is that for every agent, I have a valuation function that assigns a value, a non-negative value, to all the subintervals of 0, 1. So I look at any interval I, look at any agent A. So VA of I is the value that agent A has for this interval I. I am going to work with this setup where the valuations are induced by density functions. So you can think of like every agent has a probability measure, like without loss of generality, a probability measure over the unit interval. And the valuation is obtained by considering the area under the curve of this density function. So I integrate with respect to agent A's density function, and I get the value for this interval I. So we again, the talk is not too notationally heavy, but this is something I'll keep on using. So V subscript of A just means the valuation of agent A. So subscripts are always going to denote the identity or the index of agents. So that's the valuation of agent A for interval I. If I were to pick another interval, say J, as shown on the screen, and BA of J again is the value that agent A has for this interval J. And this is obtained by integrating with respect to A's density function. So area under the curve just gives me the value that.
So basically, if it was just a homogeneous resource, then this density will be the uniform density. Is that how we should look at it?
Yes. Yeah.
Yeah.
Yeah. Yeah. Exactly. Yeah.
So one more thing, sort of economists are often interested in the exchange economy, right? So the individual box and fair division might be competitive equilibrium from equal division of endowments and all those kinds of. So this is not really captured in that, is there? I mean, I'm not. I mean,
no, there are no transfers if that's what you are referring to. There are no transfers. It's just that, yeah, there's no exchange here. It's just yeah, it's everyone has a.
it's just a way of. I mean, at a formal level, you're just dividing resources, right? So it's, I mean, there is a way in which you can embed the, unit square to the unit interval and stuff like that, and you might, your preferences over all bundles, you might be able to. You might be able to sort of project onto the unit interval, but they won't be well behaved necessarily. The utility functions over the unit interval, I'm not sure would then satisfy many of the, at a formal level, it's the same problem. I mean, it's the same problem. I mean, you're dividing one unit of resource here, one unit of resource there. You have some utility over all commodity bundles and so on. So now the thing is, can you project it into one, into a unit interval, the unit square? And of course you can do it, but this function which is well behaved over R2 might not be well behaved over 0, 1 or over the unit square or something like that.
among other things, but yeah, I mean, I would imagine. So if you're looking at, for example, this competitive equilibria with equal incomes,
Yeah.
they are slight. I mean, they are incomparable in certain ways. So while there, for example, if I were to, like, typically, if I were to give you half a fraction of one good, your value would scale linearly. That those sorts of properties would go away here. But like in particular, uh, yeah, like the equilibrium idea does not really uh, like there's no prices, nothing. It's just I mean, okay, let me say it this way. So in terms of dividing, say, a resource which is a square,
Hmm.
and just let's look at two things, like dividing, let's say, a square instead of a unit interval,
Hmm.
and this CEI concept. So the square to unit interval is somewhat that translation does happen. Like you can project on, and if you start out with a well-behaved valuation function, this sort of projection onto interval remains well behaved, and so you can probably translate results back. The CEI to here is a bit more is a bit more challenging. In particular, like for CEI, you can use like these Eisenberg-Gale kind of convex programs to find them, at least in the when the resources are divisible. Here, it's not obvious that you can write like a convex program to solve this problem. In fact, general, you can't. I'll tell you a negative result that sort of rules out such formulations.
Fine. Yeah. Thanks.
It's okay. But
And
yeah,
Siddharth, all the sets will be intervals throughout, right? I mean, whatever agents get or the partitions.
I am, for the purposes of the talk, yes. So every person is going to get an interval. I am looking at a problem where I want to give every person a piece of the cake and not crumbs.
Okay.
So no halwa, only pieces of the cake. Yeah.
Right.
But the other version is also interesting, and I'll just tell you one. Like in a few slides, I will tell you another. Like just as a side note, I'll tell you a result on that. But I am looking at a more challenging question where I do want to assign intervals. Yeah, so I'm making life harder for myself by imposing this extra constraint. And this does make sense, for example, in the context of, say, allocation of land or, say, processing times on machines. I do want contiguous chunks of, like this requirement of contiguity, that is, everyone gets a connected piece, is important in those applications. So, but yeah, I'm going to
And the
conclude.
valuation function, does it satisfy any regularity property like modicity?
I am only going to assume that the density function is integrable, Lebesgue integrable. Um, and so that's about it. Yeah. So nothing beyond that. Though again, for the purposes of the talk, I'll not delve into those details. So if you want pretty like something that works throughout, and in fact something weaker will work, but just think that these valuation functions are continuous over these defined over the intervals. So yeah, non-atomic and so on, but just, yeah. So there's some density function for agent A as shown here. This is going to be integrable, and using this, I get this valuation function. That's all I need. So the integrability of A's density is the only technical condition I require.
I have a question here. Are we assuming any sort of depreciation when we are dividing the resource, or it's
No, it's just additive.
okay?
So if I give
All right.
you interval J, your value is VA of J. No externalities, nothing. So you get this piece of land, J, you have a density function. You, based on that, you look at the, integrate with respect to this density function. That is, look at this area under the curve. So this shaded region, and that is VA of J. That's what you get. It's very simple model. I mean, yeah, quite bare bones. This is good. I mean, I think it's a good point to discuss this before I move on. Okay,
I think let's go
sure.
ahead.
Excellent. So what is the setup at hand? I have n agents. So as I said, agents refer to the participating so entities in this fair division exercise. Every agent has its own, is endowed with its own density function. So here is A's density function. This is agent B. This is her density function. And so both the agents evaluate the intervals that are assigned to them based on these density functions. So the VA of I comes from A's own density function, VB of J would come from B's density function. So I have these agents, they have their density functions, and my goal is to find n intervals of the cake, subintervals. So to make n minus 1 cuts and assign these intervals across the agents such that fairness is achieved. And I will define fairness in a minute. But do note that the subscripts again just denote the index of the agent that receives an interval. So I have n agents, I'll make n minus 1 cuts. That is, I'll get n intervals. And say in this picture, the leftmost interval goes to agent A. So I label it as I of A. Then the second interval from the left goes to agent B. So I label it as IB and so on. So I want to find n intervals and assign them across the n agents. So I want to partition this divisible heterogeneous resource, this unit interval, across the n agents. And the notion of fairness that I'm going to work with is called envy freeness. It's a quintessential solution concept. And what this deems is that it deems a partition of the cake, a cake division, to be fair if the following red inequality holds, which says that every agent weakly prefers the interval that's assigned to it over any other interval. So do note that the left-hand side and the right-hand side of this inequality are both evaluated with respect to agent A. And so what this inequality says is that agent A looks at the value it has for the interval that's assigned to it, that's VA of IA, and that value is at least as much as the value agent A has for any other interval IB. So A is happy with the interval assigned to her, and she doesn't want to swap with anyone else. So you have n choose 2 inequalities here. For every pair of agents, you have this inequality, and this, if this holds for a collection of intervals, then I'll say that that collection is envy free. No agent envies any other agent. So this is
You're not
the
allowed to throw away anything, right? I mean, an idea often is that you throw away a little bit of the cake. There is a trivial solution in that case. You throw everything away. But I mean, there is no sense of approximating it by, not getting the sum exactly equal to 1, but approximately equal to 1 by throwing away a little thing. Can you make the problem easier?
yeah, so there are some results that like do achieve that. So it's like what you're talking about is like free disposal. I throw away while say maintaining that the social welfare or is safe is not too bad from the optimal. But for the current problem, again, I'm just keeping a high benchmark and saying this has to be a complete division of the cake. Yeah, so nothing is thrown out. I just assign the whole cake and still achieve this. And as you said, like there's a trivial solution. I mean, I could just throw away everything. Uh, yeah, I guess paupers don't envy each other. So that would be one like fair solution. But here I do want the entire cake to be partitioned. Yeah, so no free disposal. But this is the fairness definition I'm going to work with, and it says that yeah, if there's no envy in the among the agents. So as I said, like the only sort of the two things that you'll have to keep in mind for the talk is this idea of VA, what this means, and this is the definition I'm going to work with. Rather kind of clean and simple, but that's the desiderata here. I want to design an algorithm that finds such a NB-free, like finds such a cake division. So at this point of time, and this is like, if you haven't seen this before, it's rather not obvious that such a division exists. In particular, with like very limited assumptions on VAs, it's non-trivial to assume that such a division exists. So the first result I'll talk about is this classical proof, like a proof from the book by Su, that shows that in fact under very mild conditions, under mild assumptions, such a division of the cake is guaranteed to exist. It's a beautiful proof by that uses Sperner's lemma. I'll sort of go through it. There are two reasons for me to sort of present the proof. The first one is that it's quite elegant. The second one is that it also highlights the fact that at the level of generality, like without any assumptions, the proof is somewhat non-constructive. So I'll present the broad general result, and then I'll sort of get to our work, which makes certain assumptions about the density functions and hence these VAs, and shows that under those assumptions for those subclasses of the cake division problems, you can design efficient algorithms. So I'll start off with proving the sort of universal existence of NB-free divisions. And as I said, it follows from this result called Sperner's lemma. I'm sure many of you have seen this. Sperner's lemma is a sort of, can be thought of as a combinatorial analog of Brouwer's fixed point theorem. And in fact, the computational analog of this problem is hard for this complexity class called PPAD. So in particular, the computational version of Sperner is as hard as finding fixed point of functions, or finding Brouwer's fixed point, or say computing Nash equilibrium. So computationally, it's a hard problem. The lemma is in itself, again, gives a universal existence result, and I'll talk about the lemma first and then connect it to NB-free divisions.
So one question.
Yes, yeah.
So this existence is with regards to a connected allocation. I mean, this.
Yes. So I
There
am.
always exists a connected allocation which is NV3. That's the result under
That's,
these mild.
yeah,
Oh.
Yeah, like that. But to be kind of interestingly, if you ask, like, is there a simpler proof for disconnected? I don't have that.
Okay.
So in complete generality, the existence of NV-free, the result is through this Sperner's lemma, or like you can also use 6-point theorem, but like that's just a change of guise. But the result I'm going to talk about requires each of these I1s, so I1, I2, IN, all of these to be connected intervals. Yeah. And yeah, pretty much throughout the talk, I'm going to stick with this connected intervals. I'm not going to talk at all about disconnected ones. I can circle back to it. There are, if you allow for approximations, it does simplify the problem a bit. Yeah, and so you can get simpler results if you were to not allow it, were to allow some sort of this free disposal and all that. So there are other ways, approximation results become easier, but I want to work with this harder problem of assigning everyone a connected interval. So in terms of designing the algorithm, I'm going for a more challenging task with this additional requirement of every agent getting a connected interval. Okay, so let's start with Sperner's lemma. I'll take 2 minutes to recall, and if you haven't seen it, tell you what Sperner's lemma is, and then I'll connect it back to the existence of NV-free cake division. So I'll connect it back to cake division. So what is Sperner's lemma? Well, the lemma deals with simplices. So for simplicity of exposition, let's just look at triangles. So I'm looking at the case of 3 agents, so n is 3, and I'm looking at the convex hull of the 3 basis vectors. So in particular, I'm looking at this simplex in R3. So these are all the vectors whose components are non-negative and they sum up to 1. Sperner's lemma deals with simplices. This is in R3. I mean, with the right level of technical generalization, and you can extend it to Rn. I'll just, again, easier to draw pictures, so I'll just deal with R3. And what is the connection with cake divisions? Well, if you look at the set of all possible cake divisions, that's nothing but the simplex, right? So if I pick any point, say x1, x2, x3 in this simplex, so this identifies a cake division where the leftmost interval is of length x1, the middle interval is of length x2, and the right interval is of length x3. So do note that this point x1, x2, x3 gives me a partition of the cake. It gives me 3 intervals. It does not specify the ownership. It does not say that the leftmost interval has gone to which agent. It's just one possible way of cutting the cake. So in particular, the topmost vertex here is a cake division where the leftmost uh, interval is pretty much the entire cake. So the second and the third intervals are of length 0. Similarly, the bottom left point 0, 1, 0. This one is a cake division where the entire cake is just in the second interval, the leftmost interval and the rightmost interval are of length 0. So every point in this simplex is a potential cake division and vice versa. So that's at a high level the connection between like why Sperner's lemma is applicable in the cake division context. But Sperner lemma deals with a triangle, like a simplex and a triangulation thereof. So I start off with the simplex, I break it up into small subsimplices, so these baby triangles. And the Sperner's lemma is a result that deals with such a, given any triangulation, it kind of deals with this setup. So here's a convention I'm going to follow. It's a convention, and this is sort of the prerequisite, so to speak, for the Sperner's lemma. The convention is a coloring scheme. So the idea is that I will always color the leftmost component. I'll associate with the leftmost component the color red. I'll associate the second component with the color yellow and the rightmost component with the color blue. So in particular, all 3 of these extreme vertices of the triangle get 3 different colors. So I'm just setting things up towards the Sperner's lemma. This is a convention if you're dealing with Rn. If you have n agents and you're looking at the simplex in Rn, then you'll have n colors. So that's how things generalize. For R3, I have 3 different colors. Okay, what Sperner lemma says is that if I were to start off with the simplex, start off with any triangulation of the simplex, so I break the simplex, break the triangle up into a bunch of baby triangles, and I were to color the vertices, these vertices that you see on your screen, in a legal manner, then something interesting will happen. So let me tell you what is a legal coloring. Well, the legal coloring is pretty much the convention that I told you. So the top vertex gets the color red, the bottom left vertex gets the color yellow, and the bottom right vertex gets the color blue. Every vertex on the edge, on the left edge, joining the red and the yellow vertex, have to be colored either yellow or red. So these 2 vertices get one of these colors. Every vertex on the bottom edge has to get a color of its, again, the 2 endpoints, so either yellow or blue. And here again, you can assign these 2 vertices any 2 colors, but they have to be either red or blue. Let me sort of summarize this in the following manner. I can color a vertex, I can assign a color to a vertex such that the color is associated with a non-zero component, right? So the left component is, the first component is red, the second component is yellow, and the third component is blue. So if you look at the top vertex, it's only the first component is non-zero, right? It's 1. So I have to give it color red. If you look at the left edge, the only 2 non-zero components are the first or the second one. I mean, because these 2 points I hope my arrow is is visible. It is. So these two vertices, the non-zero components are either the first one or the second one. So these guys can get a color of either yellow or red. Here in this particular case, I've given this guy a color of yellow and this one a color of red, and so on. So pick any vertex in your triangulation, look at the non-zero components and assign any color associated with the non-zero components. Do note that all the vertices in the interior of the triangle, interior of the simplex, all the components are non-zero. So for them, I can assign any arbitrary color. So in particular, this vertex right here in the middle can be assigned any color in Sperner's lemma. And let me, for as an example, color it as yellow. What Sperner lemma tells me is that if I were to give you such a legal coloring, if I were to give you a coloring that conforms to these rules, then there will always exist a triangle, a baby subsimplex, where all three colors show up. Okay, let me just repeat that one more time. What the result is saying is that do note that the coloring legality actually only forces a condition on the boundary of the triangle. The vertices inside can be colored in an arbitrary manner, but as soon as you give me like a a triangulation with a legal coloring, there will be a small triangle, a baby triangle, where all the three colors show up. So it's a universal existential result. Um, and in this picture, for example, here is the subsimplex, the baby triangle, where all three colors, red, yellow, and blue, show up. So the diagram doesn't do justice to the generality of the lemma. Like imagine a triangulation with many, many points inside the simplex, and those points you can color arbitrarily. What the lemma says is that it doesn't matter how you cover those internal vertices. If the coloring is legal on the boundary, you'll always have, there's a universal existence of one of these trichromatic baby simplices, such a subsimplex where all the three colors exist is guaranteed to be there.
So could you explain the connection of this color scheme with the cake cutting thing? I think you were saying something, right? That the leftmost, rightmost, and the central components are red,
yeah,
blue, and yellow.
Give me 2 minutes. I'm actually going to do that in the next slide. So right now,
you haven't commented on that, right?
No, okay. No, not. So all I'm right now saying is what is Sperner's lemma. If you have seen this already, then yeah, I just wasted a few minutes of your time. But nonetheless, yeah, just to be inclusive, I reminded everyone of what Sperner's lemma is, and this is it. Yeah, and you can use this to, for example, prove Brouwer's fixed point theorem. And as I said before, the computational analog of it, which kind of corresponds to finding like this trichromatic baby simplex, that's considered to be a hard problem. Like it's complete for this class called PPAD. So as hard as say finding the Nash equilibrium. Okay, so that's Sperner's lemma, and now, as was asked, let me now connect it back to cake division. I start with the simplex, which is the space of all cake divisions. There's one more ingredient I'll need, and this ingredient is complementary to its sort of, it's in parallel to Sperner's lemma, so don't mix the two. I have Sperner's lemma, just keep a mental note of that. I will start with a triangulation which has one additional property, which is that every vertex has an owner. As one of the agents is the owner of the vertices. So in particular, here's an example. Like if you look at this triangulation, and I've labeled the vertices with the owner, like the owner agent. So the top vertex here is owned by agent 1. This vertex is owned by agent 2. This vertex is owned by agent 3, and so on. The property I want out of this ownership is that if I look at any baby subsimplex, then all the three agents show up. So again, like I will not talk about how to generalize it to like Rn, but you can use, say, for examples, Kuhn's triangulation, and along with that, you can come up with this ownership labeling along with the triangulation. So I start off with a simplex triangulation such that every vertex has an owner. The property is that if I look at any baby subsimplex, then all the 3 agents show up. And in general, in Rn, all the n agents will show up. So, okay, with this, I will start coloring the subsimplex, the vertices. And to do the coloring, I'll actually just go to the agent that owns the vertex and then ask her for her preference. So what do I mean? I mean that, let's say I look at the top vertex here, which is owned by agent 1. I'll go to agent 1 and then say, okay, if I were to propose this cake division, which of the three pieces would you prefer? And her reply is going to be in a colored manner, in the sense that if she prefers the leftmost, she'll say red. If she prefers the middle piece, she'll say yellow. If she prefers the rightmost, she'll say blue. So this is again the convention that I had mentioned. Left is red, middle is yellow, right is blue. So at the top vertex, the cake division is 1 0 0. The entire cake is just in the left piece. So of course, the agent is going to say red. Similarly, this, if you look at the bottom left vertex, this is owned by agent 1, and the cake division that you propose to her is going to be 0 1 0. So she's going to prefer the middle piece, which contains the entire cake. And so the coloring response from agent 1 is going to be yellow. Here, for example, I have agent 3, and this is the cake division, where the third piece is of length 0. It's on this edge on the left. So this agent 3 is going to either say the left piece or the middle piece. In this case, red means that agent 3 prefers the left piece. So here is the entire backdrop. The sort of everything is now set in place. I have this triangulation. I have these, start off with the triangulation with these ownerships, and I just color the vertices using the preferences of the agents. The key observation here is that if I were to do this, I would in fact end up with a coloring that's legal in the Sperner sense. The coloring that will come out of it will satisfy the requirement of Sperner's lemma. And the point exactly is that you'll never assign a color to a 0 component, right? The components that are of 0 length, you'll never assign that the color associated with that. And so what you get is that if you apply Sperner's lemma, there is going to be a trichromatic triangle, a baby subsimplex where all the 3 colors show up. The labeling, the ownership labeling also tells me that all 3 agents show up. So now, again, this picture is rather big, but imagine this trichromatic baby simplex to be arbitrarily small. What you get is that there are these cuts that are arbitrarily close to each other, but in these cuts, the agents prefer different pieces. So imagine like taking finer and finer triangulations such that this 3 vertices come closer and closer to each other. And then what you get is a cake division where all 3 agents prefer 3 different pieces. And hence that corresponds to an envy-free division. There's a limiting argument here, and the technical assumption of, say, for example, the continuity of VI gets used here. So you can formally use, for example, say, the Bolzano-Weierstrass theorem and like plug in these limiting arguments, but intuitively, like if you look at a fine enough triangulation, that gives you a cake division which is NV free, because all the 3 agents are preferring 3 different pieces in that specific division. So that's the connection to cake division. That's how you use Sperner's lemma to prove that a NV free cake division always exists. Does that answer your question, Siddharth?
Yes, Siddharth, it does. And yeah, the continuity things that you said are because the evaluation functions are density driven and acting over the interval, right? So
yeah, so you start off with an integral.
Assumptions are all met.
Yeah. Exactly.
Okay, thanks.
It's a bit more general, like you can, you don't need that. You can work with a slightly ordinal preference. If Sue's result is slightly more general, but for now, for at least for the model at hand, this certainly works.
Yeah.
What does the ownership basically mean here? Like, how do we interpret ownership at these three vertices?
I'm kind of not, all I'm saying is I start off with a triangulation where this is just given to me. What I do want, so imagine that this baby simplex is rather small. I do want to solicit preferences from all the three agents. And that is what the ownership tells me. So I start off with a triangulation with the ownership. I pretty much don't even look at the valuations, and I then color them. So these are two sort of independent pieces. There's no interpretation to it. It's just a requirement for me to get to NV freeness. In particular, if not all the three agents showed up, I could not have argued that this, I mean, imagine that this trichromatic subsimplex is arbitrarily small. Then I could not have argued that all of the agents are NV free. So in particular, like if you squint and think of this, all these 3 points as being arbitrarily close or in fact the same, this says that here agent 1 prefers yellow, i.e. the middle piece. Agent 2 says red, i.e. the left piece. And agent 3 says blue, i.e. the right piece. So all three are pointing to three like different pieces, three different intervals. And if you just assign it that way, they will be NV free.
Right.
Does that make sense?
Yes. And it does not, whoever lies on the three vertices, like here, one has an ownership on all the three vertices. So it's possible that it can be 1, 2, 3 or 2, 2, 2 or whatever. Like it does not matter where the ownership lies. You will always find a subsimplex inside which will have all the three people inside.
No. I start off with a triangulation where that property is satisfied. So
Okay.
yeah. The thing that I'll get out of the Sperner's lemma is the trichromaticity of it. The coloring is what I get out of the Sperner's lemma.
Okay.
I start off with a triangulation along with this labeling. So
Yes.
I don't care about the extreme vertices. So the triangulation I start out with has two properties. It's a triangulation, and every baby simplex has all three agents. And my point is that you can construct such a triangulation in general in Rn using, say, for example, Kuhn's triangulation, or even barycentric. You can label in a particular manner to get this. So such triangulations exist. I'm just giving that to you as a fact. With such a triangulation, I will get the coloring from the preferences and then apply Sperner.
Right.
What happens if an agent is indifferent over two shares?
I can break ties arbitrarily. It doesn't matter.
Okay.
Yeah. So I mean the fact that I always have trichromatic suffices. Yeah. The ties can be broken arbitrarily.
Okay.
I mean, yeah. Didn't show up in the proof at all. Excellent. Okay. So long. And so what I have is this very nice result of Su that under these mild assumptions, and specifically like to say the continuity of VI, I always have an NV free cake division, i.e. I've connected pieces for the agents such that no agent envies anyone else. So those VA, IA greater than or equal to VA, IB holds for all pairs of agent. And the punchline is that this is non-constructive because I'm sort of using Sperner's lemma to get to it, which in itself is non-constructive. I mean, from an efficiency point of view. Okay, so that's sort of the good news in terms of universal existential result. Let me now switch gears a bit and talk about finding such NV-free divisions, that is looking at the algorithmic side of things. So the Stromquist actually showed that the fairy tale ends here, in the sense that, in fact, there's no finite time algorithm for finding NV-free cake division. So this is a result that works with an adversarial model and it has this like the precision and all do count here. Still, it's a strong negative result. It says that while such divisions always exist, they're out there, finding them, there's no, let alone a polynomial time or an efficient algorithm, there's no finite time algorithm for finding such NV-free divisions. And even if you were to relinquish this contiguity requirement, that is, say that every agent gets a connected interval, I'm now, just for this sentence, leaving that requirement aside. Even if you do that, the best known algorithm is actually hyper exponential. It's like the n to the n, like 6 times. It's the towers of n. So even for 4 agents and all, this just starts running into like number of stars or something. So this is a really there's a large gap, even let alone a polytime. This is the best known algorithm for finding NV-free divisions, even if you were to allow disconnected pieces. So this is a very nice result by Aziz and McKinsey. So with this backdrop of a sort of very general existential result and strong negative results is where we start. And what we do is like now say that, okay, in general, the problem is hard. Can we identify interesting instances, like broad class of interest instances where the problem is tractable? That is, I want to identify a meaningful class of cake division instances where I can have efficient algorithms for finding NV-free divisions. There's a slight technical issue that the result we have gives you NV freeness up to arbitrary precision. That is, you get NV free up to a exponentially small factor eta. After the talk, I can sort of discuss this technical detail, but for the purposes of the talk, I'll just ignore this detail. I'll not belabor it too much. You can drive eta exponentially small. So this is somewhat similar to convex optimization issues. Like you can get arbitrary close, but not exactly. And sort of, again, just to say it in one line, the cuts can be at irrational points. So if you're looking at, say, like bit precision issues and so on, this will come up. So
I think rational approximations are the key, is it?
Yeah, so I can give you instances where even the input is completely rational, but the unique NV-free solution happens at irrational cut points. So when you output that with a finite bit precision, you will lose out eta. So even with the rational approximation, there'll be some small exponential loss, and that's morally, that's what's happening here.
Fine.
Okay, so that's the result. I will talk about an algorithmic framework for algorithmic result for finding NV-free divisions. And what is the, so when I say broad class of instances, well, the way we capture this is by this property called the monotone likelihood ratios property. I will define it. Again, this is a property of distributions that do show up in mechanism design. Nonetheless, I will formally define it, but let me give you some examples that fall under this property. So examples of instances that are sort of captured by our result. So the use cases for us are going to be like number of named distribution families. So FIs again denote the density of the agent. So the valuation is obtained by integrating with respect to FIs. So say, for example, I give you a cake division instances where the densities of the agents are Gaussians with different means, but the same variance. Then I'm here to define what monotone likelihood ratios property is, but in that case, the property holds and we can apply our result. So one way to see this specific instantiation is that these are like single peak preferences. Every agent has a most preferred point, which is the mean of the Gaussian. And as you move away from the mean on the cake, the density drops as a Gaussian. So the variances are the same across the agents, but the means are different. These kind of instances are captured by the property, monotone likelihood ratios property, and hence our results will apply to it. Another example is the case of linear density. So say all agents have linear density. So VIs are again obtained by integrating these FIs. Even then, this property holds and our results apply. Similarly, binomial as a polynomial, exponential, many sort of, in fact, like linear translations of log concave densities satisfy this property. And so there are many named families of distributions which are encapsulated by this property. And so just by looking at this property and in this unified manner, we kind of solve the problem of finding fair divisions for all of them. Okay, so what is MLRP? What is this property of monotone likelihood ratios? The idea, let me just define it for two densities and then I'll generalize it to n densities. And as the name suggests, the property deems that two densities, say Fi and Fj, satisfy MLRP, the monotone likelihood ratios property, if the likelihood ratio, the Fj by Fi, is non-decreasing over the cake. So it's kind of easy to see in this figure. Let's just look at F2 and F1 and F2. So if I look at the likelihood ratios, that is F2 by F1, at 0, it is less than 1. F1 is more than F2. At some, when they intersect, the likelihood ratio is exactly equal to 1. The ratios is, both are equal. And when you move to the right, F2 is more than F1. So this ratio has gone above 1. So as you move from 0 to 1, as you move from left to the right, this ratio of F2 by F1 keeps on increasing, and hence F2 and F1 satisfy this property, which is called the monotone likelihood ratio property. So MLRP. Yeah, and sort of a calculation to check that the other examples I've mentioned here, like the Gaussian and so on, they do satisfy MLRP. Now extending this to beyond two densities, I'll say that a collection of n densities satisfy this property if the consecutive likelihood ratio, so Fi plus 1 by Fi satisfies this property. So Fi plus 1 by Fi is non-decreasing for all I. So F2 by F1 is non-increasing, F3 by F2 is non-increasing, Fn by Fn minus 1 is non-decreasing. So if I give you such a collection of densities, then I'll say that they satisfy this property, they bear MLRP.
This is a single crossing property of these densities, basically.
Among other.
You can order the densities in a way so that the consecutive ones don't cross each other more than once.
So that is implication. I don't think that's
also it's slightly stronger than that, basically. Yeah.
It is stronger than that, yeah. But it certainly is a single crossing. It does imply, like, yeah.
So is it related to that, what is it called, this monotone comparative statics of integrals, this MLRP property? I mean, for divisions.
Stochastic dominance implication, which I'll say in a minute. But
yeah. Something like that. I mean, in the context of integrals.
So right now I'm just defining it for densities. And whatever the VI is just the integral of that. Right. But I will give you an implication of this property, which we establish and use, and that's quite hauntingly like a stochastic dominance thing. But okay, intuitively, what this says is that if you look at Fi plus 1 compared to Fi, it's putting more mass to the right. Right. So as you move towards the right, Fi sort of relative to Fi plus 1 is sort of increasing as you're moving from 0 to 1. It does imply single crossing, but it's certainly not, it's not required to be, say, unimodal and so on. in particular, if I were to give you identical FIs, all the FIs were the same, then this property would be satisfied. And that's a trivial case for cake division. Nonetheless, you can just pick any F and let's assume that all agents have the same F. And this property would be, because the ratio is always 1. Okay, so that's the property. Do note that I've stated in terms of like I and I plus 1, but it is transitive in the sense that if it will hold for fj and fi for any j more than I. Furthermore, the ordering here is implicit. That is, I'm assuming that the agents are indexed in such a manner that this property holds. So agents are indexed such that the consecutive likelihood ratios bear MLRP. Okay, so that's the property I have. What I actually need from you to keep a mental note is actually the following implication. And as I said, intuitively, what this property says is that compared to fi plus 1 is putting more mass to the right of the cake. And here is an implication. I'm not going to prove it. The proof is in the paper. But what the implication says is that if I were to give you densities that satisfy MLRP, then I'll have the following stochastic dominance per interval. What is this property? Well, it's saying the following. So let's pick any two intervals L and R. So any two intervals in the cake where L is to the left of R. Right. So these are disjoint intervals. The interval L is ends before the right before the interval R starts. And what this, if I have densities that satisfy MLRP, the property that holds is the following: that if I look at the value that agent I has for R and normalize it by the value, the total value, that is the value of L union R, then that is at least as much as the value that agent I has for interval R, and again normalized by L union R. So if I were to normalize both agents by the total value they have for L union R, then I plus 1, the agent I plus 1 puts more value on R. So if you were to take L union R as the entire interval, so the denominators would then become 1, you get stochastic dominance. This is a stronger property. This is saying that up to normalization, this holds for any interval L and R on the cake, L being to the left of R. Again, I'm sort of not going to prove this formally to you, but intuitively, this is kind of following from the fact that fi plus 1 is heavier on the right side of the cake. And again, recall that VIs are obtained by integrating with respect to FIs. So if you don't want to like carry along the burden of FIs, this is the property I'm going to use for my algorithmic result. This is all I want you to keep a mental note of. I mean, again, this is completely expressed in terms of the valuations. In fact, I am going to instantiate this for a very specific case and just use that. And here's a useful instantiation where what I do is, I mean, while the property holds for any pairs of intervals L and R, let's start with two intervals which are of same value for agent I. So I start with two intervals L and R such that I is indifferent between the two. Now, what I'm claiming here is that if I were to then assign the left interval to agent I and the right interval to agent I plus 1, then then there will be no NB between the two agents. Well, why is that? Well, from I's perspective, this is kind of direct because I is indifferent between the two intervals. So if L is given to I and R is given to agent I plus 1, then she's certainly not going to NB I plus 1. She's indifferent. On the other hand, if you just were to use this inequality and look at the left-hand side, the left-hand side is is half. So the denominator is Vi of L plus Vi of R. Vi of R is equal to Vi of L. So this ratio on the left-hand side is exactly equal to 1/2. Again, you expand the denominator out as the sum of the values that agent I plus 1 has for L and R. If you simplify, what you'll get is that Vi plus 1 of R is at least as much as Vi plus 1 of L. So agent I plus 1 values R at least as much as she values L. So this assignment gives you an NV-free solution. Let's just keep a mental note of that. In fact, this will let me get to the key grand idea of our result. It will let me define a new solution concept that will kind of lead to NV-freeness. So with this mental note of this implication, let me define our key construct, the sort of the light bulb of the paper, which are what are called ripple divisions. So what I'm going to do is define a new division, which on the face of it looks simpler than an NV-free division. But what I'll show to you is that this sort of seemingly simpler construct is actually enough to guarantee NV-freeness when I have MLRP. In fact, when I have that implication that I mentioned in the previous slide. So what is a ripple division? So I'll define, so this box is a definition, I'll define a collection of cuts, these points to form a ripple division. If the ith interval from the left and the I plus 1th interval from the left are of equal value for agent I. Okay, this is a mouthful, so let me just parse through it step by step. So what the definition says is that these points, x0 at 0 and xn at 1, they form a ripple division. If I look at the, let's say the two leftmost intervals, x0 and the one between 0 and x1 and the one between x1 and x2. So the two leftmost intervals, and they are of equal value with respect to agent 1. So under V1, these two intervals are of equal value. If I look at the next two intervals, so the second one from the left and the third one from the left, they are of equal value for agent 2. So now with respect to V2, so on and so forth, till I get to the ith interval Vi, where the ith interval and the I plus 1th interval are of equal value for agent I. So I just keep doing that for all the n minus 1 agents, enforce this inequality. If this holds, then these collections are said to form a ripple division. So let me now, in fact, name these intervals and assign them. So I look at a cake division obtained by assigning the leftmost interval to agent 1, the second interval from the left to agent 2, and so on. So I just go in order, assign these intervals, and I'm now going to argue that they actually form an NV-free division.
Siddharth, just
Yes.
a time warning. I mean,
Sure.
of course,
5 minutes.
You have 5 minutes, but you can go on for another 20 minutes. It's not a problem.
No, I'll just maybe 5-10 minutes.
Yeah, that's fine. That's fine. So I don't want to. I mean, I just wanted a heads up. That's all.
Sure. Yeah, I'm pretty much like ramping down now.
Yeah, thanks.
Right. So these are the intervals I have, I1 through In. I've assigned them to the agents. And what I'm going to argue is that they actually form an NV-free division. So yeah. Okay. So let's do that. Yeah. Somehow the keys are not working. So do note that if I name them as I1 through In, the equalities, the defining inequalities turn out to be this. So agent 1 is indifferent between the interval it has and the interval that's given to agent 2, and so on. So every agent I is indifferent by definition between the interval it has and the interval to the agent on its right. Okay.
So such a partitioning exists. Is that clear, or am I missing something?
I haven't spoken to it, so let me just show that this is useful, and then I'll show that it.
Okay.
Yeah, you're right. I mean, I'm kind of punting on that for a few slides. But let's say, I mean, yeah, you're right. Like, at this point, I don't know if they exist, but what I'll show is that if they do, then they do, like they are NV free. And the rationale is pretty much from this instantiation of stochastic per interval stochastic dominance that I had. In particular, let me prove it very quickly for agent I plus 1. So I'm going to prove NV freeness for agent I plus 1. Towards that, let's look at interval I sub I and interval I sub I plus 1. By the definition, by the design of a ripple division, these two intervals are of equal value for agent I. And hence, if I were to like invoke that implication, what I'll get is agent I plus 1 actually values her interval at least as much as she values the interval of agent I. So I have this inequality here in yellow. This is again because I is indifferent and I plus 1 is on the right, satisfying MLRP. Now I can actually chain this argument. In particular, I can now look at interval I sub I minus 1 and interval I sub I. So this I sub I minus 1 is the left interval L, this I sub I is the right interval R, and I'm looking at agents I minus 1 and I plus 1. So not agent I, but I minus 1 and I plus 1. And again, the same kind of an idea would again the same implication would instantiated to this setting would give me that I plus 1 actually values I sub I more than I sub I minus 1. And if you were to chain this, what you'd get is that yeah, okay, something is happening. Right. So if you were to chain these inequalities, what you would get is that as you move from I sub I plus 1 to its left, the value keeps on decreasing. So agent I sub I plus 1 does not envy any agent to its left. It's rather symmetric. I'll sort of spare you the details and you can kind of show that even to the right, you'll not have envy. So all in all, what you get is that triple divisions do imply NV freeness. So these are like certainly interesting divisions to look at. Do note that in contrast to an NV free division, the definition here entails only n minus 1 equalities. I'm only looking at sort of consecutive agents and forcing equalities, n minus 1 of them. In contrast to that, NV freeness entails looking at n choose 2 inequalities. So even in that sense, this is a simpler solution concept. Now the important question at hand is, okay, fine, they do imply NV free divisions, but do they exist? Or furthermore, can I find them efficiently? And I'll quickly wrap up by showing that both these things are true. In terms of existence, here comes the key observation, which is that as soon as I give you the first cut point x1, right, if I were to say magically tell you what the first cut point x1 of a ripple division is, you are done. In the sense that all the subsequent cut points can be simply obtained by composing these equalities. In particular, I'm saying you start off with any cut point x1 prime. Go to agent 1 and ask her to make x2 prime such that this equality holds. So you feed x1, ask agent 1 to, using her valuation, to find x2 prime. Now that you have x1 prime and x2 prime, you go to agent 2 and ask her to cut x3 prime, again forcing this equality, and you ripple down, and hence the name ripple division. As soon as you start with x1 prime, you can chain these equalities and keep finding the next and the next and the next cut points. The key aspect that you do need to have is that the last cut point, xn prime, must fall at the end of the cake. So xn prime has to be equal to 1. In particular, say if you were to start at 0, that is x1 prime is 0, then all the cuts will be 0. Right, all the agents will just keep making the subsequent cuts at 0. On the other hand, if you were to start very close to 1, certainly this process would not complete. You'll run out of cake before you would have had a chance to ask all the agents to make a cut. Nonetheless, under a technical assumption, it's a mild technical assumption, what you can show is that this is a continuous function of the last cut point is a continuous function of the first cut point. Like as soon as you make x1, x2, x2 prime is a continuous function of that, x3 prime is a continuous function of the previous two, so on and so forth. So what you can show is that this function f, which maps the first cut point you pick to the last cut point you have, is continuous. Now all you have to do is apply intermediate value theorem to argue that there indeed exists, there necessarily exists a point x1 such that the last cut point is at 1. And that is nothing but a ripple division. That is, so this, you get the universal existence of ripple divisions via intermediate value theorem. And this is what I had alluded to in the beginning. I have now, if you look at the two boxes, these two results, I have shown you the universal existence of NB-free cake divisions, not by Sperner's lemma or not by Brouwer's fixed point theorem, rather by a very sort of mild-mannered intermediate value theorem. So I mean, intermediate value theorem is fixed point theorem in one dimension. Nonetheless, by this simple, much simpler hammer, I am able to guarantee the existence of ripple divisions, which under MLRP are, I have shown you that they are indeed NB-free. So this new sort of existence result for this class MLRP is now like going to give me a algorithm as well. In particular, for the algorithm, I just need to find this x1. I have the function f can be calculated just by looking at the valuations of the agent. So all I have to do is like find an x1 such that if I ripple down, xn lands at 1. So again, the existence follows from intermediate value theorem, and hence under MLRP existence NB-free follows from intermediate value theorem. And finally, how do you constructivize it? How do you get an algorithm out of it? Well, you just apply binary search to find your x1 such that the entire cake gets rippled out, partitioned by this ripple division thing.
And that binary search is executed up to some precision or
exactly, and that's the data that we get.
That's the data, right? I mean, essentially, we are thinking of dyadic divisions or something of the interval, maybe.
Exactly, yeah. Like but you don't have to like, do it sequentially. You can do a binary search. So you can, yeah, you're right. It's a dyadic division of the thing. By binary search, you can like zoom into x1 to a fairly, yeah.
And what about this f thing? I mean, in the algorithm, I mean, how do you do computations about this function f? I mean, is there an oracle or something? Or
yeah, so again, this I haven't really spelled the details out, but the way the standard way that the valuations are given is through an oracle. It's called the Robinson thing. So you just need oracle access to these valuations, and so you go to the oracle for v1, feed it this in like start at x1, like look at the value for 0 x1, and then find an x2 such that this equality is met. So you just need oracle access, and you're good to go.
And those are the theta1 assumptions. I mean,
those are the like the Lipschitz const, like those are Lipschitz. That's the assumption. So I'm assuming that the f is Lipschitz continuous, and the Lipschitz constant is like not super exponential. That's the technical assumption. Yeah. But for the examples I mentioned, like Gaussian, linear,
those are parametric, I mean, anyway. Yeah.
So for them, it's satisfied. But even if I give you Oracle black box access to the VIs, the algorithm can be executed.
Right.
Okay. Yeah. I think I've gone over time. But yeah, that's sort of the summary of it. Binary search, you can find ripple division, and under MLRP, these are guaranteed to be NV-free, and hence you get an efficient algorithm for finding NV-free cake divisions in this MLRP world. Let me just flash these additional results I have. In particular, you can show here that fairness comes without loss of efficiency. That is, every every NV-free cake division in this MLRP setting is Pareto optimal. Again, details I'll be happy to talk about offline, or certainly in the paper. Bunch of interesting immediate open questions. But yeah, let me just stop here and like thank you for your time and try to answer any questions that you might have.
Thank you, Siddharth. Very interesting talk and very clear talk also. So
Okay,
we'll be happy to take questions now. So please unmute yourself and ask questions if you have.
Hi, so let me ask on Aruna speaking from Devashish's computer. One thing, this is just completely speculative, but one thing that this reminds me of in sort of in game theory is, finding a Nash equilibrium, is typically finding a fixed point and so on. But there is there are a class of games, potential games, where finding the equilibrium, finding Nash equilibrium is equivalent to solving a maximization problem. Right. So is it, by the way, there is also a sort of interesting connection, as this paper by, what is it, the computer science paper, Karagyanis or something et al., where one NV freeness and efficiency comes from maximizing, Nash welfare. So, I mean, I'm just sort of wondering, is there some general way that one could formulate finding, there's essentially under certain specific circumstances, finding a fixed point is equivalent to finding a maximum of a single function. This is not what you are doing, because what you are doing is that you're essentially reducing, as you said, this Sperner's lemma, multi-dimensional thing into a one-dimensional, intermediate value theorem. But in general, I mean, is there something to this? I mean, some maximization which will give you NV freeness.
Yeah, so there are so for example, the point is that like the way the classification happens in let's say from these complexity classes are conceptually interesting too. So Brouwer's fixed point, so whenever you prove existence through these sort of results like Sperner or Brouwer, essentially like under the hood, there's a parity argument. There's a path following argument, and hence the name PPAD. What ends up happening is that once you show that like something can be proved, let's say instead of a parity argument by like a potential argument, which is this potential game that you are referring to. So as soon as you have this new existential result through some other total argument like parity, instead of parity you have a potential argument or like an optimization, like an optimal solution of an optimization problem, as is the case in Kargyanis's work, you do get like this new existential result opens up avenues for newer algorithms. And this is again while this is not a potential argument in this specific case, but that's sort of the insight here. Like one way to I guess at least the way I kind of see it is that, say you want to have identify a class of instances for which complexity barriers can be bypassed. So to do that, it's best to start off with trying to understand, okay, for this class, can I give a standalone proof of existence, which is simpler in some sense to the general one. And that is a good base to develop algorithms. But they are different. Like Kargyanis's result, for example, is for division of indivisible goods. And you have a recent result that sort of extends it to actually give a pseudo polynomial time algorithm for it. So this EF1 plus PO is a very dear question to us as well.
No, I was just speculating in general of the approach. Let me also say that what you're doing is essentially the way. I mean, this sort of has an echo or sort of resonance in some other work that in social choice, for instance, or whatever. The local. I mean, you're substituting. You're making what you're ensuring is that a local constraint is you're able to order the agents in such a way that you can only look at you can look at local arguments, because you're sure that the global, once the local one is satisfied, the global one, if it's satisfied for a neighbor, it'll also be satisfied for a more distant neighbor, right?
Exactly.
So again, for instance, this idea of no restoration, that what is equivalent, that small f over small, the ratios of the densities are, don't if they intersect once, then they, then one has to stay above the other, or and stuff like that. I mean, those ideas are you'll find them there as well. What are paths of no restoration, along the preferences and so on. So I mean, it's nice to see this and sort of related to broader classes of things, where again, what you're doing is essentially making sure that local constraints hold. So your the set of large set of constraints can just be substituted by a bunch of local constraints. I mean, that's essentially the idea of sort of optimal auction design as well, right? I mean, there you have an uncountable infinity of incentive constraints, but in the one-dimensional problem, you can only look at local constraints up and down, and that's good enough.
Yeah, these structural things do help a lot. And in this case, it's rather in like apparent. Like you have this, as I said, you only have n-1 equalities, and rather than I mean, this does lead to a fair bit of simplification. Yeah.
Anyway, great. Thank you.
I do think there might be other connections. So, but yeah, at least so yeah.
Yeah. Thanks.
Are there other questions? Anyone? Okay, let me ask one. So, I mean, one can also think of a multi-dimensional cake in the sense that instead of having a 0-1 interval, you might think of a square, 0-1 square, and basically, I mean, are there results on those also, existence of an NV-free allocation and so on that?
Right. So I think if you were to not insist on like very structures in those divisions, then I think projecting onto a line or something would suffice.
Okay.
But there are results that speak of like I want to divide like a square in axis parallel rectangles and so on. And there things do become harder, and there's some negative results as well.
Okay.
Yeah. So I think the papers that I have in mind are by Sigal Halevi and his group. Proportional is like I only talk about one singular notion of fairness, which is NV freeness. The things like proportional fairness and all, which are relatively simpler than NV freeness in some sense, and those again have been looked at in the square case. So even cubes and so on, but the problem becomes more challenging and interesting when you impose it's like require that every agent now gets a rectangle, like an axis parallel rectangle. So those are the
And also, I mean, your construction automatically hints at a weakening of this NV freeness, which is that suppose I divide the cake into, let's say, these intervals, then if I weaken it to, let's say, only NV freeness of the neighbor, so you can only, you may envy far away agents, but only not envy your neighbors. So, I mean, that itself is an interesting concept to study. I mean, have people studied that? I mean, in the sense that.
So do note that like the existence of ripple is completely independent. It does not require ML.
Yeah.
They exist all the time, assuming full support of the densities. So they do exist all the time. It just so happens that under MLRP they become NV free.
Correct.
But you're right. Like one thing, like if we have thought a bit, like there's no specific result, but it should kind of strengthen it. So you only are NV free between like your neighbors and so on. So there have been some results of this form, like looking at NB freeness with a social network on the agents. So like there's a graph that says these are your, so those are there, but yeah, like not quite encompassing, right? Yeah. That's an
But by the way,
interesting.
this MLRP property is pretty common in economics. The moral hazard problems,
Right, right,
the standard solutions to that would involve an MLRP assumption.
right. And this is slightly different from the mechanism design context where I am, yeah, instead of type distribution, I'm assuming them to be distributions
Yeah,
that
yeah,
induce
yeah, yeah, yeah,
population.
yeah, yeah.
That's why I wanted to sort of repeat it. Yeah.
Great, great.
Yes.
Any other
Yes.
questions? Okay. Okay. Thank you very much. Really had a great time with the presentation. Great
Thanks again for the
presentation. Uh,
invitation.
so we'll end this meeting, and I'll send you another link for the
Yeah,
meetings of the students. So
right.
Siddharth and Bhabuk, I'll also copy you for that meeting. And thank you again. Okay.
Yep.